Good morning. So in today's lecture, I will be discussing about radiation reaction and Cherenkov radiation. Let us first understand what is a radiation reaction. Radiation reaction, if you look at the Lamas formula, an accelerated charge emits radiation. The radiations which are emitted by the charged particle, it carries of energy and also the momentum away from the charge. Since the momentum is conserved, the charge after emitting radiation is pushed in the direction opposite to the direction of emitted radiation. It is similar to the recoil of the gun after firing the bullet. So here also the moment the radiations are detached from an accelerated charge, then it exerts a force, it exerts a momentum in the direction opposite to the direction of its emission. So as radiation carries out energy, the accelerated charge is expected to lose energy. So the recoil force acting on the charge due to the emission of radiation is called radiation reaction, radiation damping, self forces. Several names are given to it. So radiation reaction is nothing but the force exerted by the radiations which are emitted by the charged particle onto the charged particle itself. It is a sort of, we can say, it is a sort of opposing force acting on the charged particle. So if you consider this force for a non-relativistic particle, the velocity v is much less than the velocity of light. We can write down the formula for the power radiated by a charged particle q moving with an acceleration a to be equal to 1 upon 4 pi epsilon 0 2 by 3 q is square a is square upon c cube. If we exploit the law of conservation of energy, so from the law of conservation of energy, this power radiated by the charged particle must be balanced by the rate at which the particle loses energy under the influence of the radiation reaction force F radiation. If you recall Newton's second law of motion, normally we write down the Newton's second law of motion as the force F to be equal to rate of change of momentum. Here, once we understand the concept of a radiation reaction, force exerted by the radiations going out of the charged particle on the charged particle itself, just to conserve the Newton's second law of motion, Newton's or law of conservation of linear momentum. The force, we can write down the equation of motion as a F external plus a F radiation will be equal to m into dB over dt. So here we are considering the external force to be equal to 0, and you will see at the end. So according to the law of conservation of energy, this power which is radiated by the charged particle must be balanced by the rate at which the particle loses energy under the influence of the radiation reaction force F radiation. The work done by a force in displacing a particle by distance dr is F into dr. If you find out the rate of work done, so it will be F into dr by dt. So dr by dt becomes the velocity. So the rate of doing work by a force acting on a charged particle is F radiation dot B, and it must be equal to the power radiated by the charged particle. That is why you see there is a minus sign, because the charged particle will lose energy because of a backward force acting on the charged particle because of the radiation. So the work done or the change in energy rate at which the particle will lose energy must be equal to the total power radiated by the charged particle with an acceleration to be equal to A. So here there is one more comment that I would like to make. If you look at the electric field formula, the electric field formula consists of two terms. One is the velocity term and other as the acceleration term. But when we wrote down the Larmor's formula, we gave consideration to the acceleration term and we assumed the velocity terms to be equal to 0. But in reality, the term is not equal to 0. So if you consider the term, because of the you consider the velocity term also, then in the calculation of power by using the Poynting vector definition, E square comes into picture because it is E cross B upon mu naught, and if you substitute B to be equal to R cap cross E upon C, it is proportional to E square. It comes out to be E square upon mu naught C into R cap, if you recall the expression. So let us consider the velocity term also along with the acceleration term. So we can write the electric field term to be made up of the velocity term and the acceleration term. Remember, velocity term goes as 1 over r square and the acceleration term goes as 1 over r. That is why we call this as the radiation term, and it is long-lived also. If you take the square of both sides, so again it is finding out the vector dot product of this sum of the velocity and the acceleration field with itself. So E square now becomes equal to EB square plus EA square plus twice of EB into EA. I club these two terms together, EB square plus 2EB dot EA and EA square separately. If you look at the three terms, EB square, since EB goes as 1 over r to the power 4, r to r square, so EB square will vary as 1 upon r to the power of 4. And the second term is EB into EA. EB goes as 1 over r square, EA goes as 1 over r, so its dependence is 1 upon r cube. And similarly, EA square, EA goes as 1 over r, so it will go as 1 over r square. So if we talk in terms of the dependence in terms of r, then we can say, okay, EA will be available at the larger distance as well. Otherwise, these E square will have two terms. The energy is stored in the velocity field and the energy is stored in the acceleration field. And right now, we are ignoring the energy is stored in the velocity field. And when we write down the Larmor's formula, we don't give any weightage to the energy is stored in the velocity field. So we have to be careful about the assumptions that we are taking while writing down this equation. So the energy, in general, the energy lost by the particle in any interval of time will be the sum of the energy carried away by the radiation plus the energy pumped into the velocity field. All these terms must be taken into consideration while writing down all these things. So this is just to remind you that energy lost by the particle in any interval of time consists of maybe even small, but energy is stored in the velocity field is also there. If at an interval is considered at which the system returns to its initial state, then the energy in the velocity field is same at either end and only net loss is in the form of radiation. Then we can exploit this formula that we have written based on the law of conservation of energy, that F radiation dot B is equal to minus 1 upon 4 pi epsilon 0, 2 upon 3 Q square A square upon C cube. So we are taking a situation in which the particle comes back to its initial state. So the energy in the velocity field is same and only losses are because of the radiation. So if we consider that particular time interval, we can integrate this equation over the time interval t1 to t2. So this becomes t1 to t2 f radiation dot velocity vector b into dt to be equal to minus 1 upon 4 pi epsilon 0 2 upon 3 q square upon c cube integration from t1 to t2 of a square into dt. A is the acceleration. Acceleration is the rate of change of velocity. So I have written it as velocity dot velocity dot, because v dot is acceleration. So a square can be written as a dot a dot, sorry, a vector dot a vector, and a vector is the b dot rate of change of velocity. So we write it b dot v dot. Now we integrate this by parts. First function into integration of second. This term will also be here. So the first function is b dot as it is into integration of b dot is now b. So b dot b is now equal to t integration over t1 to t2 plus t1 to t2 into b double dot differentiation of first into integration of second into dt. This is integration by parts. If the time interval is chosen in such a way that system returns to its initial state, in that case, the contribution of this term will be equal to 0. Or even if the particle is simple harmonically oscillating or moving along a circular path, the angle between the velocity and the acceleration will be 90 degree, and the contribution from this term will be equal to 0. So we have to consider an interval in which there is no contribution or the velocity field energy remains the same. So there is no contribution from this, and we can write down this equation. So the first term is 0, and then we have 1 upon 4 pi epsilon 0, 2 upon 3, q square upon c cube, integration t1 to t2, b dot, or it we can also b double dot, or we can write down a dot also, dot b into dt. In left hand side also we have b dt dot v dt, and the right hand side also we have v into dt. So either we equate both sides or we put the two equations together. So this into dot b dt, now this will become equal to 0, and that will ensure that f radiation is equal to 1 upon 4 pi epsilon 0 2 upon 3 q square upon c cube into a dot. That means the radiation force depends upon the rate of change of acceleration with time. This formula was derived by the Abraham and Lorentz. So it is called Abraham-Lorentz formula. Abraham-Lorentz formula. As I told you earlier, basically this is a formula defined for in fact there are a lot of restriction imposed on the problem, and then we derived f radiation to be equal to 1 upon 4 pi epsilon 0 2 by 3 q square upon c cube into a dot. Let us consider a particle which is subjected to no external force. I told you in the beginning that in presence of the radiation force, we have to modify the Newton's second law of motion. We have to write down the external force vector plus radiation force vector to be equal to m into a. That is modified Newton's second law of motion. So here we are again taking a condition. We are subjecting particle subjected to no external force. So if there are no external force, then the only force acting on the particle will be the radiation force. So we write down f radiation to be equal to 1 upon 4 pi epsilon 0 2 upon 3 q square upon c cube into a dot, and that will be equal to m into a from Newton's second law of motion. So therefore this a dot is dA upon dt. dA upon dt will be equal to a upon tau. Tau is nothing but this whole thing divided by m. 1 upon 4 pi epsilon 0 2 upon 3 q square upon c cube into m is the value of tau. Now we make use of the method of separation of variables to solve this. So dA upon a is equal to dt upon tau. So we integrate it from a lower limit. Let us say at t is equal to 0, the acceleration is a 0, and at time t the acceleration is a. So the left hand side integration will be ln of a within the limits a to a0 will give us ln of a minus ln of a0. That means ln of a upon a0. And on the right hand side, we have dt because tau is constant. So it is just t upon tau from 0 to t. So that is t upon tau. If you remove natural log, then a upon a naught will become e to the power of t upon tau. So if you see the result of this equation is very interesting and very amazing also. A will increase as a function of time, which is never possible. And if you calculate the tau, the value of tau for an electron, you know the charge on the electron, you know the mass of the electron, you know the velocity of light. If you calculate this, this formula will be applicable over the time interval of 6 into 10 to the power minus 22nd, because it is just like a time constant for this. Suppose we consider a to be a0 to be equal to 0, because that could be a condition that at t is equal to 0, the acceleration is equal to 0, because we are considering no external forces acting on the particle. But if we take a to 0 to be equal to 0, then the acceleration will be equal to 0, and we will not be able to write down the relation like this. So this formula, it is strictly applicable over a time range of the order of 6 into 10 to the power minus 24 seconds only. I will advise of all of you to read the book by Griffith and the comment of Griffith also on the Abraham Lorentz formula. Then we now have to discuss another type of radiation called Cherenkov radiation. Cherenkov is the name of a Russian scientist. In fact, CE, normally we read it as Cherenkov. So in some books you will find they write down CHE also, but it's Cherenkov is CERENKOB, Cherenkov radiation. The Cherenkov radiations are similar to the shock wave resulting from a supersonic object in air. In fact, if an object in air moves with the velocity larger than the velocity of sound in air, it basically leaves a shock wave behind. Similarly, here also, if a charged particle moves through a medium with a velocity larger than the velocity of light in that medium, remember, not the velocity of light 3 into 10 to the power of 8, because in a medium, the velocity of light will become c upon n. N is the refractive index of a medium, and refractive index is related with the dielectric constant also. So if a particle moves through a medium with a velocity larger than the velocity of light in that medium, it emits an unusual type of radiation, which are called Cherenkov radiation. Remember, these are the radiations emitted by the medium due to the passing charged particle. They are not emitted by the particle. Unlike bremsstrahlung radiation or synchrotron radiation, bremsstrahlung and synchrotron radiations are emitted by a charged particle itself as a result of its environment. What is meant by environment? Bremsstrahlung radiations are the radiations emitted by a decelerating charged particle. If a charged particle is moving in a straight line, then the radiations emitted by the charged particle because of its deceleration are called bremsstrahlung radiation. Similarly, if a charged particle is moving along a curved path, then the radiations which are emitted by the charged particle itself are called synchrotron radiation. So bremsstrahlung and synchrotron radiation are emitted by the charged particle itself, while Cherenkov radiations are emitted by the material medium under the passage of a high energy charged particle. So you have to visualize the difference between the two. The radiations emitted when a charged particle passes through a dielectric medium at a speed greater than the velocity of light in that medium. So if a v is larger than c upon n, n is the velocity of light, this v is the velocity, c upon n is the velocity of light in a medium of refractive index n, and v is the velocity of light. So, in fact, when a charged particle moving with a uniform velocity v, suppose we have a charged particle which is moving with a uniform velocity in vacuum, there will not be any radiation because radiations are emitted by an accelerated charged particle. So in vacuum, it's moving, a charged particle moving with water velocity will not produce any radiation. But when the same charged particle is allowed to move with a uniform velocity v, the condition is it should be larger than the speed of light in that medium. When it passes through the medium, it emits radiations which were discovered by Cherenkov, and to honor him, those radiations are called Cherenkov radiations. These are emitted by the material medium I told you. So the fast moving charged particle passing through a material medium excites the electron of a medium. When the charged particle passes through the medium, just by a cooperative phenomena, what happens is then the electrons goes into the excited states. These excited electrons, as a result, gives out radiation in a cooperative fashion while returning to the ground state. Because you know that there are two types of radiation: radiative and radiative radiations and non-radiative radiations. So I'm talking about radiative radiations. Radiations comes out of the charged particle because when the electron comes back from the excited state to the ground state, then in a cooperative fashion, it gives out radiation. But there are certain things, they are not radiating in all the directions. There are some particular directions only in which these radiations are very prominent. So there are several ways of again understanding Cherenkov radiations, other things. Normally in your textbooks, you will find out the two ways of handling these Cherenkov radiation. One is qualitative and the other is very quantitative. Very quantitative means contour integration, Fourier transform, everything is involved to get the same result. So I am using basically a qualitative method to explain you that you understand what are Cherenkov radiation. I'm just going to give you a qualitative method to explain you that what is the direction in which the Cherenkov radiation are more prominent. So you already know that suppose we have the passage of a uniformly fast moving charged particle. What is the condition of the charged particle? The condition of the charged particle is that it should move larger than the velocity of light in that medium. So it's moving, so it's a dielectric medium, dielectric constant K. Dielectric constant K is related with the refractive index of a medium, and you know these two equations, d D'Alembert square A to be equal to minus mu 0 J and d D'Alembert square B to be equal to minus rho upon epsilon 0. We need to solve these two equations to understand radiations. That is what we have been doing since last several lectures. If you write down this equation for this particular situation, then del square A minus 1 over C square del square A over del T square will become now minus mu 0 J, and C here in the dielectric medium will be replaced by C upon N. N is the refractive index of a medium, which is K square, that is dielectric constant square. The solution of this equation, in fact, if you solve, you already know the solution of these equations are Liénard-Wiechert potential. And Liénard-Wiechert potential have a denominator 1 upon Liénard-Wiechert potential denominator is 1 minus R cap dot B over C. In fact, this has to be evaluated at T to be equal to TR. Both the electric field and the magnetic field, sorry, both the vector potential and the scalar potential has a denominator 1 minus R cap dot B over C. V is the velocity of the particle, C is the velocity of light. So in a dielectric medium, the value of a C will be replaced by C upon N. So it becomes, the denominator becomes now 1 minus V cos theta divided by C upon N. So it becomes 1 minus Vn cos theta divided by C. So in the direction where this denominator will tend to 0, the value of the potential and hence the fields will be very intense for that particular direction. So 1 minus Vn upon C into cos theta tending to 0 means the value of cos theta must be equal to C upon Nb. This is the condition, this is the direction across which the Cherenkov radiations will be observed. So Cherenkov radiations are more prominent at an angle theta to be equal to cos inverse C upon Nb, where theta is the angle made with the direction of the velocity. I will suggest all of you to see the very descriptive way of deriving the same formula cos theta to be equal to C upon Nb by using complex integration, contour integration, Fourier integration, and so on, and see the results comes out to be the same. So this is all about basically your unit 1. We started with the scalar and vector potential, and then starting from the Maxwell equations, we got the two inhomogeneous equations. We solved them for A and B. Then from A and B, we wrote down E and B. We converted those E and B in terms of the present position, and we saw that we ended up with the electric field and the magnetic field, which are not having spherical symmetry. Then we calculated basically the Larmor's formula. Larmor's formula, how is power radiated, depends upon the acceleration of the particle. We considered two different cases. The first case was when the velocity is parallel to the acceleration, and the second one was when the velocity is perpendicular to the acceleration. When velocity is parallel to the acceleration, the radiations are called linear radiations or bremsstrahlung radiations, and in case of the particle moving along a curved path or a circular path, the radiations emitted by the charged particles are called synchrotron radiations. We also derived the formula for the direction of power radiated. We saw that in case of a non-relativistic particle, the distribution of power is in the shape of a donut. It is maximum along the direction perpendicular to the direction of the velocity of the particle. But when the particle approaches to the velocity of light, those donuts are stretched along the direction of the velocity or the direction of the acceleration. And if B is exactly equal to C, in that case, the entire energy will be carried by the charged particle along its direction and the acceleration. And in today's lecture, we talked about the Abraham-Lorentz formula, that when the radiations are detached from the charged particle, they exert a force, they exert a backward force, a radiation force, we call it as a radiation force on the charged particle, and we derived the Abraham-Lorentz formula for radiation reaction by making a lot of approximations. And finally, the Cherenkov radiation. So this is all about the first unit course. In the second unit of electrodynamics, we have to deal with the concept of four vectors, and whatever we have to do, we may make use of basically the four vector. And there again, we will derive a formula called Leonard radiation formula, and in that formula, we will have basically the power radiated formula in terms of the velocity and acceleration in such a way that we can find out the power radiated whatever be the angle between the velocity and acceleration of the particle. And making use that formula, exploiting the concept of four vectors, we will derive the two special cases, one for linear radiation and other for synchrotron radiation, and we will see that they are similar to gamma to the power 6 for linear radiation and gamma to the power 4 along with the normal non-relativistic Larmor's formula, and all other things remains the same. So please go through it. So after this lecture, I will first try to give you one home assignment, and you will have to submit the solution of that home assignment, followed by the next lecture will have an examination of 1 hour in which you will be asked to solve some of the question over the given interval of time and submit it, and then we will switch over to the next unit. That is all about. Thank you so much.